Welcome to Chapter 4 of the NIMO Introduction series. This is the hands-on tutorial where we'll put everything together and run a complete materials optimization workflow from start to finish. You'll learn how to create candidate files, run multiple optimization cycles, and visualize your results. By the end of this chapter, you'll be ready to apply NIMO to your own materials discovery projects. In this tutorial, we'll optimize a simulated ternary alloy system. Our goal is to find the composition that maximizes a target material property. In a ternary system, only two composition variables are independent, so we search over x1 and x2, while the third is fixed by the requirement that the fractions sum to 1. Since we don't have access to a real robotic laboratory, we'll simulate the experiments using the Brannon function, a standard test function for optimization algorithms. In real applications, the robot would perform actual experiments and return measured values. But the NIMO workflow remains exactly the same whether you're simulating or running real experiments. The first step is creating a candidate file that defines your search space. We use NumPy to create a grid of possible compositions. In this example, we create a 16 by 16 grid, giving us 256 candidate compositions to explore. Each candidate has x1 and x2 values, plus an objective column that starts as null, meaning not yet tested. We save this as a CSV file called candidates, CSV. This file will be the central data structure throughout our optimization, tracking which candidates have been tested and their measured values. The core of NIMO is the optimization loop, which repeats for a specified number of cycles. Each cycle has 4 steps. First, select candidates using NIMO selection. For the first cycle, we use random exploration to get initial data. For subsequent cycles, we switch to PHYSBO for intelligent selection. Second, run the experiments. In real use, the robot executes these. In our simulation, we calculate the Brannon function. Third, collect the results and save them. Fourth, update the candidates file with the new measurements. Then we track our progress by recording the best value found so far. This loop continues until we've completed all cycles. As the optimization runs, we track the best objective value found at each cycle. This creates a history that shows how quickly we're finding good solutions. Typically, you'll see rapid improvement in the early cycles as the algorithm explores the search space, followed by slower refinement as it focuses on the most promising regions. At the end of each cycle, we print a summary showing the current best value and its composition. This helps you monitor whether the optimization is making progress and decide when to stop. Visualization is crucial for understanding your optimization. We create 2 main plots. The first shows all tested points overlaid on the true objective function landscape. This reveals whether NIMO is sampling in the right regions. The second plot shows the measured values at each tested point, colored by their objective value. This helps you see where good solutions were found. Notice how NIMO tends to cluster samples around promising regions rather than sampling uniformly. This intelligent sampling is what makes Bayesian optimization so efficient. To appreciate the value of intelligent algorithms, let's compare PHYSBO, BLOX, and random exploration on the same problem. We run each method for 10 cycles with 3 proposals per cycle. The results typically show that PHYSBO and BLOX find better solutions faster than random selection. While random exploration eventually explores the space, it wastes experiments on unpromising regions. PHYSBO and BLOX focus their samples where they're most likely to find improvements. This efficiency is especially valuable when experiments are expensive or time-consuming. NIMO provides built-in visualization functions to make analysis easier. The plot history function creates a chart showing how the best objective value improved over time. The plot distribution function shows where samples were taken in your search space. These functions are simple to use. Just import from NIMO, visualization, pass your candidates file, and save the resulting figure. These tools help you quickly assess whether your optimization is progressing well without writing custom plotting code. Long optimizations may need to be paused and resumed later. The tutorial adds this with two small helper functions built on standard Python file operations. The save checkpoint helper copies your current candidate's file to a checkpoint directory, preserving your progress. Later, you can use load checkpoint to restore the state and continue from where you left off. This is also useful before risky experiments. Save a checkpoint first, then if something goes wrong, you can restore to the known good state. I recommend saving checkpoints regularly, especially after completing each batch of experiments. Let's summarize the complete NIMO workflow. First, create your candidate's file defining the search space as a CSV grid. Second, run the optimization loop. Select candidates, execute experiments, update results, and repeat. Third, always start with random exploration for cycle 1 to collect initial data, then switch to PHYSBO or another intelligent algorithm. Fourth, use visualization tools to track progress and analyze your sampling patterns. Fifth, use checkpoints to save your state and resume later. Remember that candidates, CSV is your central data file, tracking everything throughout the optimization. In Chapter 5, we'll explore advanced topics including multi-objective optimization and integration with real robotic systems. Congratulations on completing the hands-on tutorial.